Hi, I'm Peter Adamson, and you're listening to the History of Philosophy podcast, brought to you with the support of the Philosophy Department at King's College London and the LMU in Munich, online at historyofphilosophy.net. Today's episode, Best of Both Worlds, Tycho Brahe. Let's do an experiment, with apologies to visually impaired listeners who may not be able to take part. Extend your arm and look at your fingertip while closing one eye. Now look at it with the other eye. You should notice that the finger seems to shift its position very slightly. Now do the same thing, holding your finger much closer to your face. You'll see the same effect, but with a bigger shift. This is called the phenomenon of parallax. I mentioned it last time in passing, but wanted to start this episode by explaining it more fully, because it's going to play such a major role in the 16th century reactions to Copernicus that will be concerning us today. As Copernicus was well aware, the parallax effect can be used to determine how far away things are. The calculation is based on the apparent difference in position of the same thing seen from two different places. These could be your left and right eyes, but might also be much further apart, say two different cities, or the same city at two different times, as the relative position of the Earth and the heavenly bodies changes. If you're a Copernican, it's the location of the city itself changing as the Earth spins and orbits the Sun. If you're in the older system of Aristotle and Ptolemy, the city stands still on an unmoving Earth while the heavens revolve above. You might be thinking that the parallax effect should have yielded powerful arguments in favor of the Copernican system. After all, that system was broadly correct. The Earth is going around the Sun, not vice versa. So you'd think anything that would provide more accurate data about the situation should have helped the case for heliocentrism. And as we'll see, parallax did help to undermine the ancient Ptolemaic cosmology. But parallax was also the basis of a powerful objection to Copernicus. One of those who articulated it was Tycho Brahe, the greatest astronomer between Copernicus and Johannes Kepler. He reasoned as follows. If the Earth is going around the Sun, then we should have a significant parallax effect as its position changes, moving all that way along its annual orbit. Yet we see no parallax at all for the fixed stars, which were assumed by most astronomers to be embedded in a single sphere at the edge of the visible universe. It rotates once per day in the old theory, and stands still while the Earth spins once each day according to Copernicus. This means that the sphere of fixed stars would have to be further away than supposed by earlier astronomers. Much, much further away. The distance between the last planet Saturn and this outermost sphere of fixed stars would be, Brahe calculated, at least 700 times greater than the distance between the Sun and Saturn. Copernicus simply admitted this consequence of his theory, and he was right. There is parallax for the distant stars. It was just far too small to see with the instruments available at the time. The tiny effect was first successfully measured in the 19th century. And the stars are, of course, vastly further away from Saturn than Saturn is from the Sun. Brahe's figure of 700 times isn't even close. Saturn is 9.5 astronomical units from the Sun, whereas the closest stars in Alpha Centauri are a whopping 268,000 astronomical units away. But even with his more modest figure, Brahe found the banishing of the fixed stars to such remote distances to be obviously absurd. It would mean that the cosmos is multiplied to many times its previously assumed volume, 300 million times as large, says Brahe, and is mostly empty, with an unimaginably vast, yet utterly useless expanse between the planets and the fixed stars, hardly compatible with the idea that God wisely gives order to the universe. That may not sound like a particularly scientific objection, but the idea that the heavens manifest divine order was taken for granted in this period. We saw that it motivated Copernicus, and we'll be seeing that it motivated Kepler too. Indeed, a pious yearning to understand God's design was the usual rationale for doing astronomy at all. With all due respect to Copernicus, Brahe, and Kepler, the figure who did the most to promote this idea was our old friend Philip Melanchthon. As part of his influential educational reform, which spread from Wittenberg along with Lutheranism, Melanchthon exhorted students to learn the mathematical disciplines which culminated in the study of the stars. The result was that Lutheran universities standardly had at least one chair of mathematics held by a professor who was typically an astronomer. By contrast, in England, where Melanchthon's ideas did not hold such sway, there was not a single university chair of mathematics in the whole of the 16th century. It was in effect much more noticeable than parallax. According to one modern-day scholar, around the middle of the 16th century, only Melanchthon could have done the Copernican doctrine the service of providing it with a far-reaching success and establishment in the educational institutions. Unfortunately for the heliocentrist cause, this was a service Melanchthon was unwilling to provide. He was not so dismissive of Copernicus as Luther was, who called him a fool who wanted to overturn the whole art of astronomy, but Melanchthon did hold fast to geocentrism. In an introduction to physics aimed at students, he satirically commented, "Some dare to say, either because of their love of novelties or in order to appear clever, that the Earth moves." This passage was revised to be less critical in a second edition, a sign that Melanchthon did value what Copernicus had done. He and mathematicians in close contact with him approved the use of Copernicus's tables for the locations of the stars, which did not involve postulating the disturbing equant assumed by Ptolemy. In fact, one of Melanchthon's colleagues at Wittenberg, Erasmus Reinhold, spent 7 years reorganizing and recalculating these tables and published the results in 1551. Melanchthon was also in close contact with other mathematicians like Georg Rheticus, Copernicus's student and the first to promulgate his new teaching. Melanchthon appointed him to a chair of mathematics at Wittenberg. Rheticus, of course, defended heliocentrism as an account of the real arrangement of the cosmos, but Melanchthon and many of those in touch with him adopted what has been called the Wittenberg interpretation. This meant employing Copernicus's mathematical models without admitting that the Earth moves. Which brings us back to the issue we considered while discussing the opening address added by Osiander to Copernicus's On the Revolutions. As we saw, Osiander seemed to be saying that the diagrams and calculations of mathematical astronomy are to be taken in a merely instrumental sense. They should be used as tools to do things like predicting the position of a planet on a given night, while keeping an open mind about what is really going on up there in terms of spheres, epicycles, motions, and so on. Melanchthon seems to have had a similar idea. He said to his students, "The listener should understand that the construction of so many orbs and an epicycle was thought out by geometers to be able to show the laws of the planet's movements and periods, one way or another, and not because the devices in the sky are this way, although it is agreed that there are such orbs." And he cautioned them not to be confused by the use of various hypothetical constructions by astronomers. The youth should know that they do not dare to affirm such theories. While such remarks would gladden the heart of Pierre Duhem, there are reasons to doubt whether Melanchthon, Osiander, and others were really instrumentalists, like Duhem was. Aside from the completely different motivation and cultural context, it should be borne in mind that we are only talking about astronomy here and not all the sciences. A realist about, say, chemistry or the physics of sublunary bodies might still worry that our access to the stars is so indirect that we cannot do more than devise hypothetical constructions compatible with our observations. As Nicodemus Frischlin wrote in 1586, God the Creator placed these bodies so far away from our senses that we are unable to produce principles of demonstration for them as we can in the sciences of other things. In other words, we can only ever offer a fine-grained account of the phenomena to be explained without being able to grasp the causes of those phenomena. Religion might give our astronomers one good reason to be modest in their claims. While the study of the stars does bring us closer to God, only revelation really unveils the mysteries of his providence. A more technical reason would be that multiple inconsistent models might all be compatible with what we observe. In such a case, there would be no basis for choosing one model over another. By the same token, though, you might be more confident in accepting just one model if you could eliminate the other possibilities. Which brings us back to parallax. Not in the work of Brahe, I promise we are getting back to him soon, but in that of Michael Maestlin, a teacher of Kepler at Tübingen, where Maestlin took up the chair of mathematics in 1583. Along the same lines as we've just seen in Melanchthon, he admitted that no one is able to ascend into the ethereal region where he would see everything in person. So we lack causal explanations in astronomy. Yet Maestlin thought that he could use observations to show the falsity of Aristotelian cosmology. As luck would have it, this period saw a series of remarkable astronomical phenomena. A new star, or nova, visible in 1572, as well as comets that became visible in 1577 and 1580. These caused a lot of fuss. There are about 100 works just on the 1577 comet, still extant today. Meslin appealed to parallax measurements to argue that these striking new bodies were located above the sphere of the moon. In one fell swoop, he was able to dismiss the literally ancient idea that the realm of the stars was made of unchanging matter. He would still admit that mathematical astronomy cannot establish physical reality, but physics has at least to be consistent with astronomy. The two are independent disciplines, but that doesn't mean that they're allowed to contradict one another. Which brings us finally to Tycho Brahe, who is notable for both his achievements in astronomical mathematics and his innovative physical cosmology. He was a member of a noble family in Denmark, where Lutheranism and Melanchthon's educational ideas had both spread by the time of Tycho. By the way, his Danish name was Tige. Tycho is a Latinization. He went to Germany for his studies, spending time in Leipzig and Wittenberg, and famously getting his nose cut off in a duel while at Rostock. He would henceforth wear a prosthetic made out of precious metal, which, fortunately, Brahe had in abundance. He persuaded the Danish king, Frederick II, to lavish upon him a fiefdom on the island of Hven, as well as extravagant financial support, equivalent to 1% of the annual revenue of the kingdom. Now, as a member of the Danish nobility, Brahe was always in a position to receive funds from the state. In fact, he could have lined his pockets more effectively by becoming a politician and courtier instead of an astronomer. But he was determined that he would use the silver spoon he'd been born with to make a stir in science. He built a fabulous house on Hven with astronomical observatories and commissioned a series of instruments for measuring the heavens, quite literally the best that money could buy. In his tellingly named Instruments for the Restoration of Astronomy from 1580, he describes 22 of them, these being only the most impressive and important. Of course, we're still not talking about telescopes here, but about things like a brass-covered sphere model of the heavens, and more importantly, sighting tools for measuring the positions of celestial bodies at different times. He also made the same observation with multiple assistants and multiple instruments to ensure maximum exactness. The expense of these instruments was closely tied to their effectiveness. Brahe dismissed work done by others with cheaper rulers of wood because they were too imprecise. His house, called Uraniborg, was thus a state-of-the-art scientific facility, and not just for astrology. Brahe was also interested in medicine and alchemy, and was powerfully influenced by the Paracelsian movement. His basement contained a chemical laboratory with multiple furnaces, and by his own admission, he spent as much time on the discipline of alchemy as he did on astronomy. He saw the two disciplines as closely linked, with the same relations and structures appearing in the sky above and the elements here below. He thus referred to alchemy as terrestrial astronomy. But it was astronomy of the celestial kind that made Brahe's name both then and now. He was scornful of astronomers who looked at books and tables rather than making their own observations. The restoration of astronomy, he remarked, must derive not from the authority of men, but from reliable observations and demonstrations based on them. Good as his word, during Brahe's time on Hven, he took measurements of the heavens an average of 85 nights a year. This would mostly have been during the winter months when the nights were longer. When working on a specific problem, his activity could be feverish, insofar as standing in the cold Danish night, very carefully making sightings using expensively assembled instruments could be described as feverish. For example, when trying to check Venus for parallax, he took nearly 1,000 observations over 5 days, in sessions lasting 5 to 8 hours. He took on assistants to help with the work. He wrangled with fellow mathematicians in heated disputes, maybe that was to stay warm, and when he was troubled with paper shortages and printing problems, he simply set up his own paper mill and printing press. His aim was to produce a wealth of observations more accurate and ample than any that had yet been made. For this sake, he applied methods that, while not entirely unique to him, were applied with unprecedented care. For example, he would take multiple observations and use an average to avoid errors in individual sightings, and he measured the effects of the refraction of light by the atmosphere so that they could be eliminated from consideration. If all Brahe had done was to amass this data, he would earn an important place in the history of science. Kepler joined him as an assistant at the end of Brahe's life, and after legal struggles with the Brahe family, got access to his papers after the great man's death. Kepler would benefit greatly from access to this information to produce his almost literally earth-shattering theory of elliptical orbits. But Brahe assumed that his legacy would revolve around his own cosmological theory and not just the data that supported it. This was designed to be a cosmology that could avoid both the mathematical absurdity of Ptolemy and the physical absurdity of Copernicus. The absurdity he lamented in the Ptolemaic system was the same one that had bothered Copernicus, the postulation of equants, that is, a celestial sphere rotating around a point other than its own center. Furthermore, the epicycles required to make this system work seemed unfeasibly large. As for the Copernican system, he was a great admirer of its author. He called Copernicus a second Ptolemy and put a portrait of Copernicus on the wall at Uraniborg, a treatment reserved only for the true greats, including, of course, Brahe himself. But he could not bring himself to accept that the Earth moves. Apart from the problem of parallax and the incredibly distant fixed stars, he was unconvinced that bodies falling on a rotating Earth would seem to move straight down. Such rotation also struck him as inappropriate to the very nature of the Earth. It is likely that such a fast motion could not belong to the Earth, a body very heavy and dense and opaque, but rather belongs to the sky itself, whose form and subtle and constant matter are better suited to a perpetual motion, however fast. As Brahe thought about how to avoid the pitfalls of these rival world systems, he also sought to preserve the advantages of each. While the ancient cosmology seemed to maintain physical common sense, Copernicus's could explain why the planet's motions seemed to track the sun in the way I mentioned last time. This led him to propose a new set of hypotheses which would offer the best of both worlds, the so-called Tychonic system. It's similar to schemes proposed by other thinkers in this period, but is usually associated above all with Tycho, which is just as Tycho would have wanted it. According to him, the Earth stands still while the sun goes around it, as Aristotle and Ptolemy said, but all the other planets orbit the sun, as Copernicus had said. The only exception is the moon, which all agree orbits the Earth. Thus, we have a system that is geocentric overall, but heliocentric when it comes to Mercury, Venus, Mars, Jupiter, and Saturn. Brahe was proud of this new theory, but hesitated before putting it forward, in part because he had not managed to avoid all the problems that afflicted the Aristotelian Ptolemaic system. In particular, his system implied overlapping spheres, which he himself deemed ridiculous. The solution came to him thanks to the nova and the comets, which he, like Maestlin, recognized as celestial bodies that had suddenly appeared well above the level of the moon. How could this be? Brahe's answer was that the heavens are not made of impenetrable spherical bodies, as had been supposed since antiquity. Instead, the matter there is fluid and allows planets or comets to pass right through. Heaven, he wrote to fellow astronomer Christoph Rothmann, consists of a substance that is very clear, very thin, and very fine. This makes the courses of the 7 planets free so that they move without any slowing. Again, like Maestlin, Brahe considered the manifestation of the comets to have disproved the hypothesis of solid spheres, and he duly put forward his own Tychonic system as a better hypothesis that was consistent with all the observed phenomena, though not necessarily proved beyond doubt. He defended this hypothetical approach when he encountered the Parisian philosopher Peter Ramus in Augsburg. Ramus, whose own objections to classical Aristotelianism we'll be discussing later in this series, pressed both Brahe and Rheticus to strive for an astronomy that made no use of hypotheses and instead demonstrates a system of the world through causes. In Brahe's view, this project was impossible, a position he held in common with Melanchthon and the Wittenberg school. Again, this needn't mean that Brahe was uncommitted as to whether the sun was really going around the Earth. He thought of his own hypotheses as the best account of physical reality, but he didn't think that this account could be securely established by mathematics and observations, no matter how plentiful, careful, and consistent. Fortunately, there were other resources available. In that same epistolary exchange with Rothmann, Brahe argued that the Bible supported his own system and not that of Copernicus. He gratefully seized on a recent translation of the Hebrew term rakia in the Book of Genesis, normally rendered as firmament, but now as expanse or even liquid. Exactly Brahe's idea about the material nature of the heavens. Against such arguments, Rothmann countered that Scripture is simply silent on the whole question. Revelation concerns itself with salvation and not science, and is content to speak in accordance with common beliefs. Brahe conceded that the Bible does not contain scientific descriptions of nature, but warned, "Let it be far from us to think of them as speaking in such a common manner that we do not believe them to be speaking truth." This exchange may suggest that Brahe was opportunistically latching onto biblical evidence that supported him, but this would be to underestimate the fundamentally religious and even apocalyptic character of his thought. Last time, I mentioned the possibility that Copernicus believed in astrology, and his student Rheticus certainly did. This was a widely held attitude. Melanchthon himself annoyed Luther by adhering to astrological beliefs. Indeed, it was the prospect of astrological advances that motivated his steadfast encouragement for astronomy and the mathematical sciences more generally. Like most fans of astrology in Christendom, Melanchthon hastened to deny that the science has any deterministic implications. The influence of the stars is real, but not so powerful that it constrains divine or human will. Not for the first time, we see Brahe aligning himself with Melanchthon on this issue. He supplied annual astrological reports to his patron, King Frederick, and was available for drawing up horoscopes on the occasion of a royal birth. Privately, he was fairly skeptical about the accuracy of such individual prognostication, though. At the global scale, things were different. He was confident that the nova of 1572, followed by those comets, were a divine mystery and a sign of God, predetermined by him at the beginning of time and now finally exhibited to the world, which is hastening towards its evening. Along with a great planetary conjunction in 1583, these were portents of massive political disruption, with especially dire and well-deserved consequences for Catholics. Tycho Brahe was convinced he'd discovered the arrangement of the world, and only just in time, because it might be ending soon. Of course, he was wrong, and not just about the apocalypse. Brahe would have been astonished, and I think probably devastated, to learn that the young mathematician who signed up as an assistant in Brahe's last years would go on to eclipse him in the history of astronomy. This was Johannes Kepler, who didn't even have good enough eyesight to do the sort of exacting observational work to which Brahe had devoted so many frigid evenings. But he kept his eyes and his mind open, and realized that the Copernican hypotheses could be improved by dropping one more ancient assumption. A few episodes back, we looked at Lipsius. Next time, we look at ellipses, as Kepler finally puts an end to all the circular reasoning here on the History of Philosophy without any gaps.